Well, good morning, gentlemen. Today's lesson is on what we call implicit differentiation. Um, and we're going to be talking about how to find the derivative of a function that's defined implicitly versus explicitly. So let's just get started. And I'm recording this ahead of class time in hopes of the recording not being near as long as class time. Okay? All right, so the following is the graph of an implicit relation. Okay? X squared plus y squared equals 25. And we'll talk a little bit more about what implicit means in just a few minutes. So we have a circle, right? We have a circle with center at the origin and radius of 5. And the first question in our little exploration here says, tell why this relation is not a function. Okay, so if you think back to Algebra 1 and you want to know like how to tell if a graph is a function, remember you want to pass the vertical line test. That means if I can put a vertical line anywhere on the graph and touch 2 points at the same time, then I am not a function. So this is definitely not a function. But the vertical line test is not like an official mathematical explanation for why it's not a function. What makes it not a function, why the vertical line test works, is because let's say we put a vertical line from this point down to this point. Okay, now I know I can't draw very straight lines here, so that's why I just mark those 2 points. What happens is they have the same x value, but they have 2 different y values. Okay, and so and that actually would happen multiple times on here, but that's the main reason why this graph or this relation is not a function. It's because there is more than one y value for an x value. Okay, now the next question says, let's confirm that the graph is reasonable by calculating the values of y when x equals 3, and then showing that the corresponding points, plural, are on the graph. Okay, well, the function was the circle x squared plus y squared equals 25. So they want us to confirm, right? Just figure out what you get when you plug in 3 for x. So we're going to square our 3, and we're going to solve for y. Okay, and so when we subtract 9, we get 16, and when you take the square root, remember you get plus and minus 4. So the x value of 3 gives me 2 different y values. All right, and so again, we want to show that those points are in fact on the graph. So I come up here and I go to positive 3, and I have a point at 3, 4, and 3, negative 4. Okay, so we will get rid of that. All right, so we've confirmed that. All right, well, let's talk a little bit more. All right, well, it says the phrase y is a function of x means that if a value is chosen for x, then a value of y can be found. Well, explicitly defined functions are written in the form of y equals an expression with only x in it. Okay, so for an example of explicit, right, would be something like y equals I don't know, 3/5 x minus 4. Okay, where y is on one side and x is the only variable on the other. Another example might be y equals 1 over x. Okay, and so that's what it means to be defined explicitly, where y is on one side and x is on the other. And you can find y, you can find the value of y using just substitution. Okay, but in the above problem, right, in order for us to find y, we had to actually like move things and take square roots to get y by itself. So we say that that would be a function that was defined implicitly, all right? Because y cannot be found directly when x is chosen. You actually had to do some solving work. We say that y is an implicit function of x. So other implicit functions, right? Really, it's anything where you would have to do some sort of manipulation to the equation to get y by itself, where you have even though these, if you actually look at them, if you spent the time to get y by itself, these would be the same two equations, but this one is defined explicitly where y is already by itself, and this one is implicit where you would actually have to do some moving of the x and dividing and all that stuff. So if I did the same thing over here, right now y equals 1 over x is explicit, but if I were to go back to x times y equals 1, then we would call that an implicit function, okay? All right, so that's just what explicit and implicit mean. All right, so now we're going to start talking about some other things. So it says calculate y when x is 2, okay? So if x is 2, right, we're using this equation here, we get 4 plus y squared equals 25. We're going to solve real quick. Y squared equals 21. And so y equals plus and minus the square root of 21. All right. And it says, is there more than one value of y? Yes, right, because we took the square root, so we have plus and minus. And then it says calculate y when x equals 6. So we're just going to do it again. So 6 squared is 36. All right. Oh, this time we get negative 11. And in this class, please understand that we only work with real number values, not imaginary. So we just say that has no solution. And so what does this result show you about the domain of x? Well, the domain of x is restricted, right, to I mean, you can look here, if you do the domain, if you go from left to right, it covers all the x values from -5 to +5, but nothing outside of that in terms of x values, or y values for that matter. So it just shows you that x equals 6 is outside of that domain, okay? All right, so then we go on to say we need to resolve the contradiction with problem 1 and the statement that y is implicitly a function of x. A small portion of the graph is a function. Oh, right, okay. For example, if we only take the portion of the graph in the first quadrant, then y is a function, okay? So when we look at our original statement, it's not even a function. But we keep saying that y is implicitly a function of x, and so we need to kind of restrict it to where we're looking at a piece that actually is a function. So let's just take this portion in the first quadrant. Then we could actually say y is a function of x. So let's identify some other portions of the graph where y would be a function. Well, if we take any single quadrant, then we would be looking at a function. We could actually take the entire top half of the circle and it would still be a function, or the entire bottom half of the circle and it would be a function. Just understand that you can't take sides. You can't take like the entire left, because then it still wouldn't pass the vertical line test. You can't take the entire right, it would not pass the vertical line test. So there's lots of different separate options to be a function here. All right, so on a small portion of the graph, y is a function of x, so it does make sense to find the derivative of a function defined implicitly, even when many implicitly defined relations are not functions, okay? So we're getting into the derivative stuff. All right, well, number 6 here says estimate the rate of change of y with respect to x, right? So that's just fancy words for saying estimate the derivative of y with respect to x at the point 3, 4. Now I want to show you proper notation for the derivative at a point when you're using this notation. Looks like this. All right, and we want to approximate this from the graph. All right, so how do I approximate the derivative at a point? Well, we go to that point, 3, 4, and we try to approximate the slope of the tangent line there, right? We try to approximate the slope of the tangent line. All right, now I guess if I extended this a little bit more, I don't know, it looks like it could almost be 1, right? If I go from here to here, it's almost 1. So let's just say it's approximately 1, okay? Whoops, I'm at the wrong point. Hold on. 3 positive 4 is up here. All right, so maybe that's approximately -1, maybe a little bit less than that. But we're just approximating, but it actually does kind of look like it could be a little bit less than 1, or should be -1. All right, so the one I actually did first was this next one. I did 3, -4. I didn't mean to do that one first, but and that's the one that we said was approximately 1. If you wanted to put like a fraction that was a little bit smaller than 1, that's certainly fine, because it wasn't perfect. Remember, we're estimating. All right, and then the next one says estimate the rate of change of y with respect to x at the point -5, 0 from the graph. Okay, and before I write an equals, let's go up here and look at it. All right, so -5, 0 is here. All right, and think about if I were to draw a tangent line to the circle, it would be vertical. It would be vertical, okay, because it's on the side there. So keep in mind that the slope, we don't actually say equals undefined. We can just say is undefined, right, because our tangent line is vertical. All right, so let's just keep progressing through our exploration here and see where it takes us. All right, so we will now find an equation for the derivative of y with respect to x by differentiating implicitly with respect to x. Okay, so this is the meat of the lesson. So we start by differentiating the equation, taking the derivative of this equation on both sides with respect to x. So you have to be real careful because we're going to have to pay attention and observe the chain rule. Okay. All right. So let's first just take the derivative of the left and we're going to do it in pieces. So the derivative of x squared with respect to x, all right, well, since it's an x, right, we take the derivative, it's just 2x. And then I guess technically the chain rule would be like times the derivative of x with respect to x. So times dx over dx, which is 1. Okay, so when you're taking the derivative with respect to x and the variable is x, you just take it like normal. Okay, all right. Now, according to our exploration, we're skipping over to the derivative of 25. Well, that's just a constant, so we get 0. All right, but then here's what we're talking about with the chain rule. When you're finding the derivative with respect to x of a variable that is not x, we have to observe the chain rule, which means we're going to take the derivative with respect to the y, because it's a y, right, in our function. So we're going to take the derivative of y squared, okay? But then we have to observe the chain rule by taking the derivative of the y, the piece that was raised to a power with respect to x. All right, but that just means we're going to multiply by dy over dx. So it's a notation thing. All right, so what I'm saying here is anytime you take the derivative of a variable that is not x, you take the derivative like normal, power rule, product rule, whatever it requires. But then you have to multiply by the chain part, which is the derivative of the variable you're working with with respect to x. Okay, so if this was, like I'm just saying, like if this was, I don't know, m cubed, and I wanted to take the derivative with respect to x, all right, so I would take the derivative of m, right, but then I would have to multiply by the derivative of m with respect to x, okay? And so it's just a notation thing, but it's very important when you're taking the derivative of implicit functions, okay? So I'm just, again, it's a notation thing. All right, so let's put all of our parts together. All right, so the derivative of x squared was 2x. The derivative of y squared was 2y times dy over dx, and the derivative of 25 was 0. And so now let's take that equation and solve for dy over dx. Okay, so let's see, that's going to require subtracting 2x and then dividing by 2y, and the 2's will cancel. Okay, so that wasn't too bad, right? All right, well, now we have the derivative of our function. Okay, dy over dx represents, right, the derivative of y with respect to x. The derivative of our function is negative x over y. Well, now let's use this formula to find the actual rate of change at the point 3,4. Okay, so remember we approximated it on the graph, but now I want to find the exact. All right, well, this is my derivative. So if I wanted the derivative at a point, you're going to plug in, now you have an x and a y to plug in, right? Well, remember earlier we approximated it to be -1, but I told you it kind of looked like it was actually a little bit less than that. So if you wanted to choose a fraction less than -1, just a little bit less, that's a pretty good approximation. So the second part here says, is this answer consistent with the answer you got earlier? And it definitely is, because it's pretty close to -1. Okay. All right, let's keep going. All right. All right, so let's say, what does the formula give you for dy over dx if you substitute in 1, 3? Okay, well, remember, we got negative x over y, so we get -1/3. Well, does this answer have any meaning for this curve? Okay, well, let's go back to our graph. Let's find the point 1, 3. All right, 1, 3. All right, and now think about where that is, and then think about the question. Does this answer have any meaning for this curve? Well, no, because the point's not on the curve. All right, so please understand that. No, because 1, 3 is not on the curve. Okay, so you do have to make sure that when you're finding values at points, like it actually is on the function. Okay, all right, so let's find an equation for y explicitly in terms of x. All right, so we're taking a step back from the derivative for just a second, and I want us to solve for y. All right, so remember, this is implicitly defined because y is not already by itself. They want us to get y by itself so that it is defined explicitly. So I'm going to subtract x squared, and then I'm going to take the square root. Please keep in mind that you still need a plus and minus. That's the only way you're going to get the top half of the circle and the bottom half of the circle. All right, and so technically, you know, we do get two answers here. Please understand that the positive square root, right, you do have to know a little bit about graphs, right? The positive square root would give me the top half of the circle, and the negative square root would actually give me the bottom half of the circle. Okay. All right, now it says find the dy over dx using the formula. All right, so now we want to go back, all right, to the skills we already have. All right, I want to find the derivative with respect to x of the explicitly defined function I have here. All right, so that's going to require us thinking about the square root as being the power of 1/2. So then I'm going to bring the 1/2 down, right? I'm just doing the power rule. I'm subtracting a power, and don't forget the chain rule. You need the derivative of what's inside. All right, and so let's simplify a little bit. The 1/2 and the 2, when I multiply them together, they will reduce out. And so I end up with a negative x, and then I'm going to move my piece with the negative exponent down to the bottom. And let's go ahead and turn it back into a square root. Okay? All right, now let's do the same thing with the negative square root. So we have a negative in front, but then we still apply the power rule, same as before. 1/2, we need the chain rule. And this time our two negatives cancel and give me positive x over the square root. Okay, so that's my dy over dx for each one. All right, but what I want to show you is how does that come out to be the same as the dy over dx equals negative x divided by y. Okay, well, how is that the same, even though it looks very different? Okay, well, let's take a look. The square root of 25 minus x squared, right? Isn't that, and I'm comparing these two right here, right? Isn't this square root of 25 minus x squared, isn't that equal to the original y? All right, and so technically my dy over dx is in fact equal to negative x over y, because y is equal to the square root of 25 minus x squared, so I can use some substitution, and now I get the same dy over dx as before. Well, does that work for the other one? Well, let's see. Well, in the other one, when I compare, right, the square root of 25 minus x squared almost matches, but there's a negative. Well, let's move the negative to the other side. And then the square root of 25 minus x squared is equal to negative y. And look at that. That's also negative x divided by y. So you actually do get the same derivative. All right. So now I want us to use the formula we just found in the previous problem, right? The negative x over the square root, or the positive x over the square root, to find the rate of change dy over dx at the point. All right, so we keep doing the same thing, but we're doing it with different formulas. All right, at 3, 4. Well, you do have to be careful with that, because you have to understand, like, where is 3, 4 on the circle, okay? And so in terms of the circle that we had on the previous page, positive 3, positive 4 was in the first quadrant, or the top half of the circle. So when you plug this point in, you have to make sure that you're plugging it into the derivative that we got from the top half of the circle, which we said was this positive one here. All right, so we plug in the x value. All right, now, even though it says we're finding it at this point, remember, the derivative that we're using only had x's in it. So you only have to worry about plugging in x's. All right, and look what you get. 25 minus 9 is 16, and the square root of 16 is 4. So you still get the same slope we got before, or the same derivative at the point. All right, now, which method got you there faster? Okay, well, think about it. If we took the derivative after we defined it explicitly, technically we had to take the derivative twice, and we had to remember power rules and chain rules, etc., etc., etc. But when we took the derivative implicitly, right, we just had some very simple derivatives, the derivative of x squared, the derivative of y squared, the derivative of 25. And so I hope that you, and plus, okay, plus when we solve for dy over dx, it was much simpler to plug in the point as well. So I hope that you felt like, and of course it'll get easier the more you practice, but the method that should seem easier, especially after we practice some more, is going to be to, when you differentiate implicitly, okay? Now, this particular problem was not super difficult to take the derivative both ways, but the reason this method exists is because sometimes you're going to have equations that there's absolutely no way to get y by itself with only x's on the other side to make your derivative easier. So that's what this method is good for, and that's what we're going to see more of in the next exploration.